Assalamualaikum students, welcome to Electronics. I'm Madam Rosmina Zwin Abdurrahim. Okay, as usual, let's have a look on this hadith. Jabir radiallahu anhu reported the Messenger of Allah sallallahu alaihi wasallam said, "Ask Allah for beneficial knowledge and seek refuge in Allah for knowledge without benefit." Source Sunan Ibn Majah. So this hadith would like to emphasize on the importance of beneficial knowledge, okay, because some knowledge will bring us closer to Allah, and some knowledge actually will bring us away from Allah. Okay, so we always need to ask Allah to give us the beneficial knowledge that can benefit us as well as knowledge that can benefit others. Okay, now we come to chapter 3 on diode circuits. Okay, this video is about chapter 3b, which has two subtopics. Both are related to full wave rectifier. The first one is center tap transformer. The second one is bridge rectifier. Okay, for the first subtopic, which is on full wave rectifier center tap transformer, there are two things that you need to observe. The first one is on the number of diodes here. Okay, so you see two diodes here in the circuit, and another thing that you need to notice that the transformer is being tapped at the center. Okay, then it looks like we are having two loops here. The first loop involving D1, the second loop involving D2. And another thing that you should take note that it's the same, similar to half wave rectifier. When we are considering the VS, okay, the sinusoidal wave, we have the positive half cycle and negative half cycle. So the positive half cycle is represented with positive voltage. So in this case, VS, we have VS here and positive and negative like this, positive and negative like this, to represent positive half cycle. Okay, so by having this configuration, this connection, you can see that VS positive negative like this, at that time D1 will be on, and obviously at this time D2 will be off. Why? Because negative potential is connected to positive terminal of D2. And when we are considering the negative half cycle here, okay, so VS can be represented with negative and positive like this, and it's the opposite, right? Negative and positive like this. So in this condition, you can see that now D1 will be off. Okay, then this time D2 will be on. So as I mentioned just now, for the um, positive half cycle and negative half cycle. So for positive half cycle, so as we can see here, D1 will be on and D2 will be off. So that's why we don't show the loop for D2. Okay, so in this case, there will be current flowing in the closed loop. So can you see the closed loop here, right? Okay, so this is the closed loop for the loop involving D1. Okay, so from there you can get KVL equation, okay, where minus Vs plus Vd plus V naught equals 0. So in this case, V naught equals Vs minus Vd. The same thing, Vd here is actually the diode voltage. Okay, so remember the diode can be represented with the three models. If you are considering the ideal diode, this time Vd can be replaced with 0. If you are considering the second model, this Vd can be replaced with V gamma. If you are considering the third model, this Vd can be replaced with V gamma and IDRF. Okay, so this is the condition when we are considering positive half cycle. Okay, then for the negative half cycle, okay, we need to consider this loop. Okay, the first loop is not shown, involving D1 not shown because it's open circuit. Okay, for negative half cycle, we represent Vs by negative and positive like this, right? Remember, so that's why D2 will be on at that time, D1 will be off. Okay, so we are considering this loop. Okay, this loop. So it's just about the, if we do KVL, it's just about the same KVL equation, although we have another loop. In the end, we are still getting V naught equals Vs minus Vd. V naught equals Vs minus Vd, meaning to say for positive half cycle, we are getting V naught value. For the negative half cycle, also we are getting the same V naught value. Okay, so as you can see here, that's why this circuit is being called full wave rectifier because we can get the output voltage at both positive and negative half cycles. And as you can see here, the polarity of the output voltage is just the same, okay, for both negative and positive half cycles. Okay, so for example, this is the Vs, okay, the supply voltage. So if you are considering the output waveform for this particular full wave rectifier, so you can see that the positive half cycle there will be output voltage, and for the negative half cycle there will be also output voltage because we are just getting the same equation, remember? Okay, then obviously there are times when diode will be off, okay, both diode will be off. This is when Vs is less than V gamma. So when Vs is less than V gamma, although here it is under forward bias, but at that time the diode will be off, okay, then at that time open circuit, no current flow, so V naught equals 0 volt, okay, only at this time. Okay, so for center tap rectifier circuit, we can also calculate for its PIV value. Okay, so since for center tap transformer, as we know, at each cycle there will be one diode off, one diode will be on. Okay, meaning to say we can consider any loop because it will just give us the same value. Okay, for example, we consider when we are having this negative half cycle where Vs is negative positive like this. Okay, so let's have a look here where the diode is off, okay, where it can be represented with open circuit. So from here we can get one KVL equation. Okay, remember here we are talking about PIV, meaning we are considering the reverse bias condition when the diode is off. We want to know what will be the the maximum voltage across the diode so that we can choose a proper PIV value for our diode. Okay, so for this example, if we do KVL, we are supposed to get positive Vs, okay, minus positive Vs minus R plus V naught equals 0. Okay, plus V naught equals 0. Then in this case, V naught, remember V naught can be replaced with Vs minus Vd before this, remember? Okay, so that's why from here we can get Vr actually equals to 2 Vs peak minus Vd, 2 Vs peak minus Vd. So for example, if our Vs is 10 sine omega t, so meaning to say Vr here for this center tap transformer, it can be Vr, it can be 20 minus, for example, 0.6, so 19.4 volt. Okay, mean to say in this center taps transformer circuit, we need to choose a diode with PIV rating of at least 19.4 volt in order for us not to damage the diode. Okay, let's have a look for one example of full wave center tap rectifier circuit. Okay, in this particular example, as we can see here, V gamma is given and RF value is given, meaning to say we are considering the third model, and R value is given, which is 95 ohm. In this case, we are supposed to find for the peak output voltage as well as to sketch the waveform. Okay, so all the values are given, but you should take note that the value given here is at this primary voltage. Okay, so first thing to do is we need to consider the ratio of the transformer turns ratio here, okay, with the peak voltage in order for us to find for Vs. Okay, so in this case 125 volt divided by Vs equals 25. So from here we can get the 125 divided by 25. Okay, you are supposed to get 5 volt. So in this case our Vs is 5 volt. Okay, then you know that in center tap transformer rectifier circuit, if you choose any loop, at least one diode will be on, one diode will be off. Okay, meaning to say it's enough for us to consider just one loop. Okay, it doesn't matter if you want to consider the positive half cycle or negative half cycle. So in this case, let's consider positive half cycle. Okay, meaning to say now D1 will be on. Okay, obviously at that time D2 will be off. Okay, why? Because the negative voltage always being connected to positive terminal of D2. So reverse bias, right? So D2 will be off. So we are having this closed loop here, okay, involving D1. Okay, so as we know, minus Vs, if we do KVL, okay, minus Vs plus Vd plus V naught equals 0. So in this case, our V naught is equal to Vs minus Vd. Okay, and what is Vd? Vd is actually Vs minus, what is Vd? Vd is actually V gamma and Id Rf. Okay, so here we have two unknown where we don't know V naught, we don't know the value of Id, but don't forget V naught is actually equals to Id R, right? So if you rearrange this equation, you are supposed to get the ID value, then later you can get the V naught. So here is the solution. It's just the same thing that I mentioned just now. Okay, you can get the ID value from the KVL equation. Then later, remember V naught equals IDR. Okay, so you can simply get the V naught value. Okay, then you need to sketch the output waveform. So for example, this is the VS. So your output waveform obviously will be something like this. And don't forget to always indicate the peak voltage here, which is in this case is 3.8 volt. Now we come to the second subtopic, full wave rectifier, bridge rectifier specifically. Okay, so as you can see for bridge rectifier, there are four diodes in one circuit. We have D1, D2, D3, and D4. Okay, so if we do the diode analysis, it's just the same thing. Remember, if we have Vs like this, we need to consider cycle by cycle. So if you consider positive half cycle, Vs can be represented with positive and negative like this. Okay, and at that time you check, oh, if Vs is positive and negative, so D1 will be on as well as D2 will be on. Okay, because positive goes to positive terminal of the diode, negative goes to the negative terminal of the diode. Okay, then if you consider uh, the negative half cycle, okay, where now Vs is represented with negative and positive like this, and at that time you can check, oh, now D3 will be on as well as D4 will be on. Okay, so obviously this D1 and D2 will be off, meaning to say in each cycle there will be two diodes are on and there will be two diodes which will be off. Okay, so let's have a look for the positive half cycle where we are saying D1 will be on and at the same time D3 and D4 off. Okay, so if you see the loop here, okay, the current will be flowing from here. It goes through D1, it goes through the V0, it goes through the D2 and complete the loop. From there, we can get KVL equation. Okay, so as you can see, the KVL equation is given by minus Vs, okay, minus Vs plus Vd plus V0 plus Vd equals 0. So if we rearrange, V0 equals Vs minus 2Vd. Okay, so it's the same thing here. Remember, Vd can be the three models. It can be 0, it can be equal to V gamma, it can be equals to the voltage V gamma as well as the voltage across the RF. Okay, so when we consider the negative half cycle, it's just the same thing. But now D3 and D4 will conduct, will be on, and obviously D1 and D2 will be off. Okay, so we are going to get about the same equation where V naught actually equals to Vs minus 2Vd. Okay, so in this case, this is how we sketch the output waveform. For the positive half cycle, we still get the output waveform. Even for negative half cycle, we also get the output waveform. Okay, so this is called the bridge rectifier. Then how do we calculate PIV for bridge rectifier? It's just the same thing. As we know, at each cycle, two diodes will be off, two diodes will be on, right? So we are focusing on the off diodes because we are taking into account the reverse bias condition because we want to check the maximum voltage during reverse bias condition. So let's have a look for this one where Vs is at negative half cycle. At that time, we are considering, okay, D4 and D3, okay, when we are having a complete loop, okay. But since now we are considering the maximum reverse voltage, okay, so we have a look on the open circuit, okay. We are not considering the closed loop, okay, because this is for the normal analysis. Now we are having a look on the open circuit. So for the same connection of Vs, negative half cycle, we are considering the condition when the D1 and D2, which is off, reverse bias, okay. So our KVL will be involving the open circuit diodes, okay. So you get the KVL equation from here, okay. Then if you substitute everything, you are supposed to get this condition, okay. So from here we know that VR is actually Vs peak minus Vd for bridge rectifier. Okay, so this is basically the summary of PIV for all the three types of rectifiers: the half wave rectifier that we discussed before, the full wave rectifier, the center type, and as well as for the bridge. Okay, remember before this we discussed about the duty cycle, okay, for half wave rectifier. For full wave rectifier, the duty cycle calculation is just about the same. You just find for the theta 1 and theta 2, but now the duty cycle is being multiplied by 2. Okay, we are coming to the end. So let's recall for this particular video, we discussed about full wave rectifier. We discussed about the center type transformer as well as the bridge rectifier. So that's all about the video. Thank you so much. Bye.